Hello. So today we'll talk about limits at infinity. So this time it will be a different case because our x will be approaching to infinity. So given this function, let's try to consider this still involving rational functions. Say for example, so the rational function y is equal to 1 over x. So what if we will be solving for the limit of our f of x, so this specific function, but this time our x is approaching to positive infinity. So the usual thing we were doing was solving for x as it is approaching to a specific number, as it is approaching to the asymptote, or as it approaching to a specific constant. However, this time it is approaching to positive infinity. So how do we analyze that specific problem? So in this situation, what we will be doing first is, of course, we need to know that our x is approaching to positive infinity. So um, we trace where is that positive infinity going to. So if our graph is this one and this one for the rational function, so technically if it is approaching to positive infinity, it goes there, right? Because if it is going there, this specific graph will go to negative infinity because the values of x will decrease indefinitely. So that is why let's focus here, okay, to because it will be approaching to positive infinity. So if we extend this, and if you can remember with the definition, or one of the characteristic of a rational function is that the graphs of rational functions are asymptotic. So if you will be visualizing this from this specific graph, we can tell that it is asymptote to the x-axis. And so technically it will not intersect our x-axis. So if our function is approaching, or as our x is approaching to positive infinity, we can conclude that it is approaching to 0, right? So because if ever you will be analyzing as x is approaches, for example, let's start here, going here, down here until there, going there and here and here. So we tend to reach positive infinity. Again, positive infinity denotes um, greater numbers as it is increasing indefinitely. So as it increases, it tries to reach, or it tries to intersect 0, but since with the asymptote concept, it will never intersect. So technically, we can say that the limit, or the borderline of limit of f of x as x approaches positive infinity is equal to 0. Now, if ever we'll have the other way around, for example, this time we solve for the limit of our function f of x as x approaches to negative infinity. So what we will be doing here is, again, focus on the negative infinity. So technically it goes here, the other part of the graph, the other half. So say, for example, here we go there and it is approaching to negative infinity. Still, if you notice, it is asymptotic to the x-axis. So as our x, or as our values of x decreases, okay, indefinitely, it will tend to approach to 0. It will tend to intersect 0, but it will never intersect. So that is why the answer for this, if ever we'll be solving this, is equal to 0. So if you notice, both ends at positive infinity and at negative infinity, the answer will be equal to 0. So to formally introduce limits at infinity, we will have this theorem to solve. For example, you're provided with algebraic equations, or you're provided with equations without any graph. So the question is, how will we solve for the limits of those specific functions? So here, these are the concepts. So limit of x to the power of n as x approaches positive infinity is always equal to positive infinity. Also here, limit of so this will be positive infinity if our n, okay, please be careful here, with our exponent is an odd and even. So basically, there is nothing to worry about so long as it is approaching to positive infinity and x to the power of n. So it, whether if it is odd or even, it will always be equal to positive infinity. Here, if we have limit of x to the power of n, as x approaches negative infinity, the answer will be negative infinity if our n, the exponent of the function, is an odd number. So it will be negative infinity. And second to the last, we have limit of x to the power of n as x approaches to negative infinity. It will be positive infinity if our n is an even number. So if it is even, then if this is even, guys, if an x is approaching to negative infinity, it will be a positive infinity. Always remember the concept here. And lastly, everyone, say for example, you're provided with a polynomial function. So assuming this one, so limit of a polynomial function, if you can recall grade 10 topic, we have this, okay, and so on and so forth until we have a constant. This specific entire thing, this specific polynomial equation or polynomial function, if we solve for the limit as x approaches to negative infinity or even positive infinity, so it depends positive or negative infinity, it's just equal to the limit of the first term. The first term meaning the leading coefficient, or yeah, the leading term, the one containing the highest degree. So it will, so there is no need for you to solve for the limit of the remaining terms. What you will be focusing is just the leading term. The leading term meaning the one containing the highest exponent. So instead of solving all of these, you solve for just this one. Now let me provide you with some examples. So let's have our first example here. So limit of s to the power of 12 as s approaches to positive infinity. If we solve this one, so technically it's positive infinity. So nothing to worry about. So it will always be equal to positive infinity from the theorem we have earlier. Next example, for example, we have this limit of s cubed as s approaches to negative infinity. So I believe you'll agree with me that the answer for this, because this is odd and it's negative, so the answer is negative infinity. All right, next example is this limit of s to the power of 4 as s approaches to negative infinity. So careful, it's negative infinity, but this time it's an even exponent. So therefore, the answer for this is positive infinity. Now, afterwards, let's have another example. So let's have another example, which is this. So limit of 2s to the power of 5 as s approaches to negative infinity. So if we solve this, we can apply some concepts, right? So it will be 2 times the limit of s to the power of 5 as s approaches to negative infinity. So 2 is a constant, so 2 times. So if you simplify this, it's 5 negative infinity. So the answer here is negative infinity. So do not be confused if you have this 2 times negative infinity, since it's a representation that negative infinity. So it's like a scalar quantity multiplied to this thing, this with direction to negative infinity. So the answer for this is negative infinity. So what will actually prevail is the one with direction. If you will associate it with physics, this is a scalar quantity and this is a vector quantity because it indicates a direction. Right? So that's why the answer for this is negative infinity. Let's proceed to the next example, which is this. The limit of our polynomial function s to the power of 7 minus 12s cubed plus 5x squared minus 11 as s approaches negative infinity. So if you solve this, as well as mentioned, you can just treat or consider only the leading term. The leading term here is our s to the power of 7 because it's the one containing the highest exponent. So negative infinity and an odd number. So the answer for this is negative infinity. All right. So always remember that that's the last thing on the theorem we had earlier. All right, and the last example this time is we have this. So limit of s to the power of 4 minus 12s cubed plus 5s squared minus 11 as s approaches positive infinity. So again, we can just consider the leading term. And I think you'll agree with me that the leading term is s to the power of 4 because it's the one containing the highest exponent. So if you simplify this, it's a positive number with an even exponent. So the answer for this is positive infinity. So it takes practice though, but you can go ahead and go back to the theorem and try to internalize the concept so that if ever you will be answering, it will go with I mean it will go handy and it will be done smoothly. Now this time, let's have another theorem on limits at infinity. Assuming that we assume that our r, which is the exponent, be any positive integer. So here, notice it's kind of the same concept with infinite limits. It's just that the difference is our x is approaching this time to an infinity. Whereas before, for infinite limits, we are approaching to a number, to an asymptote, for example, or to a specific number where our denominator will be 0. But this time we are approaching positive infinity. So the answer for that, if you can recall on the graph flashed earlier, it's always equal to 0. It should be in this format, 1 over x to the power of r. So if we are provided with equation, we need to express the terms in terms of 1 over x to the power of r. I'll teach you how to do that. All right, another example is this limit, or under another thing for this theorem is limit of 1 over x to the power of r as x approaches negative infinity. Still the answer, so nothing to be confused with because everything here says 0, even if it is approaching to positive infinity or negative infinity. As mentioned in the graph flashed earlier, when we interpret it both from the right and from the left, it is equal to 0. So I mean, we are actually not worried with the answers because it is always equal to 0. So let me provide you with some examples on how to solve up by applying these different theorems discussed. Let's have the first one. So what if we solve this limit of s plus 6s squared all over s plus 7s squared as s approaches positive infinity. So technique though, if ever we'll be solving this, this is how I usually solve it. I don't know if it may be handy with you, but this is I usually do it. What I'll be doing first is I need to inspect whether what's the degree of the numerator, the degree of the denominator. The degree of the numerator is 2, and the degree of the denominator is 2. So if they're equal, so it's very easy. All right. So if it's equal, what we can do is we can just pull out squared. Okay. And if we pull out squared, I think we can divide s squared by s or whatever it is. So it will be, it will happen. So it will be 1 over s, right? Then plus, if we pull out s squared, it will be 6. Now, how did you do that one, sir? If you will simplify it, when you multiply them, cancel, it's s. But technically, it's just like this. The usual way is because s squared is the common exponent or the degree for both. What you'll be doing is you'll just do it like this: s over s squared plus 6s squared over s squared. And then let's say, for example, you multiply s squared outside. So that's why when we simplify, if we cancel this, what happened is 1 over s plus we cancel. That's why it's 6. That's why I got it here. But you can actually proceed to this. However, if it's very hard for you, yet you can do this process. So let's try to use this process on the denominator. So if we have s plus 7s squared, so since we know that s squared is the one, is the degree, so we can put s squared times s over s squared plus 7s squared over s squared. And s squared will be 1 over s, because if you simplify that, plus cancel, so that will be 7. So we can put here s squared times 1 over s plus 7. Afterwards, it's very obvious we can cancel them. And then we can rewrite it. So 1 over s plus 6, I'm sorry. I will write it clearly. 1 over s plus 6 over 1 over s plus 7 as s approaches to positive infinity. So what you can do, perhaps you can apply some limit rules on division. So we can have limit of 1 over s as s approaches positive infinity plus limit of 6 as s approaches positive infinity all over limit of 1 over s as s approaches positive infinity plus limit of 7 as s approaches positive infinity. So what we'll be doing here is, if you notice, the expressions now are expressed in terms of like this, in terms of the theorem discussed earlier. So to continue with this, we will be able to see that this is just equal to 0, right? Plus, this is a constant no matter where s is approaching to. Since it is a constant, so the limit of a constant will always be equal to a constant. So 6 over 0, because this is 0, plus limit of 7, a constant number, it will always be equal to 7. So 0 plus 6 is 6. 0 plus 7 is 7. So the final answer is 6 over 7. So you can run through the solution or whatever it would be. That's how we solve it limits at infinity. Technically, what the concept here, because I believe if you'll agree with me, the difficult part here is when we pull out these expression. We pull it out, it became like this. So if it's hard for you to do it automatically using this, you can apply what we were doing here earlier. All right, so well, don't worry, I'll be providing more examples. So let's proceed to the next example, which is this one. Limit of 3 plus 5y squared over 1 minus 2y squared as y approaches negative infinity. So the same thing, the same drill. What you will be doing first is to inspect the exponent, the degree of the numerator, and the degree is 2, I believe so. And the denominator has a degree of 2 still. So what we are doing is we can pull out y squared. So if it's very hard for you yet, we can apply what I mentioned earlier. So it's to the power of 2. So it will be y squared times 3 over y squared plus 5y squared over y squared. After that, it's y squared times 3 over y squared plus, we can cancel that. So that will be 5. So we can write here y squared times 3 over y squared plus 5. Now we can apply the same concept for the denominator, or we can just do it automatically. I'll teach you how I do it. So it's y squared. So it will be 1 over y squared minus 2. All right. And then we can cancel them. So what's left here is limit of 3 over y squared plus 5 and 1 over y squared minus 2 as y approaches to negative infinity. After this, you can distribute though the one we did earlier with the first example. But if you'll analyze it, we can just distribute. So limit of this one to that, you'll agree with me that it's 0, right? Then plus limit of a constant, it's 5. All over limit of that one is 0 minus limit of 2 is just 2. And if you simplify, it's 5 over negative 2, and that is negative 5 over 2. So this is your final answer. All right. So, well, if you're not comfortable having these things right away, you can also rewrite this. You can have it limit of 3 over y squared as y approaches negative infinity plus limit of 5 as y approaches negative infinity all over limit of 1 over y squared as y approaches negative infinity minus limit of 2 as y approaches negative infinity. You can do this because technically after this we know that this is 0 plus 5, this is still 0 minus 2, so you got it automatically. So it's okay if you have this step, or if it's okay that you can proceed right away to this, so long as you understand the concept. So again, the answer here is negative 5 over 2. All right, so let's proceed to another example. I believe it's the third example, third to the last, I'm sorry. So this is the next example, limit of, all right, so this is actually the tricky part. Why is it so? Because if you inspect, the degree of the numerator is 4. The degree of the denominator is 5. Okay, so they differ, which unlike earlier, the degrees are actually the same. So if the degrees are actually the same, it's very easy to manipulate. However, in this time, it is quite difficult. But let me teach you a technique and how to solve this one. The way I solve it is, since I know that the degree of the numerator is 4 and the degree of the denominator is 5, so let me just put some notation here, 4 and 5. What I'll be doing is I'll get the highest degree, all right? So I'll get the highest degree, and then afterwards, I'll pull it out. If earlier we were pulling out the common degree, which is in the example, it's like y squared, this time the higher degree, I believe, is 5. So since it's 5, what you will be doing is we pull out 5. So what will you do with that? So let's try to simplify, or let's try to pull out the denominator first so that you will not be confused. So if you pull out 5, you can do it this way. So negative 4t to the power of 5 over t to the power of 5 minus 4t cubed over t to the power of 5 plus 1 over t to the power of 5. And if you simplify, it will be negative 4 over, oh no, it's, oh, sorry, it's only negative 4 because it's both are in t to the power of 5. So negative 4 minus 4. And what will happen here will be over t squared plus 1 over t to the power of 5. So you copy that, t to the power of 5 times negative 4 minus 4 over t squared plus 1 over t to the power of 5. And let's do the same work for the numerator. However, this time, just want to tell you though, since what we did on the denominator, because we pulled out the the higher degree, t to the power of 5, what we will be doing is still we pull out the higher degree. So it's 3 to the power of 3t to the power of 4 over t to the power of 5 plus t to the power of 3 over t to the power of 5. Oh, I'm sorry. It's 5. All right. So if we solve this, cancel 4. So what's left here is 3 over t plus cancel. This will be 1 over t squared. And then you copy it here. T to the power of 5 times 3 over t plus 1 over t squared. And so afterwards, we cancel this. And then it's limit of right plus 1 over t squared over negative 4 minus 4 over t squared plus 1 over t5 as t approaches to positive infinity. So the same thing you can distribute, but if you just use the same concept, it's 1 over t. So the limit of 3 over t, I believe, is 0 plus limit of 1 over t squared is 0 over limit of negative 4, a constant, so negative 4 minus limit of 4 over t squared, I believe it's 0 plus limit of 1 over t5 is equal to 0. So if you simplify, 0 plus 0 is 0 over negative 4 minus 0 plus 0 is negative 4. 0 over negative 4 is equal to 0. So the answer is 0. All right? So that's for that example. Okay, so let's proceed. Let's proceed to the next example after this. So let's have this one. Let's have this. So this is quite a difficult one because it's very simple to look at. However, it will be very easy, difficult because we need to simplify this one first because it's 3 and it's over x plus 1, right? So it should be, if you can remember in the theorem, it should be limit of 1 over x to the power of r as x approaches infinity. So it should be only x, okay? So what we'll be doing here is, if we have 3 over x plus 1, we go to the basic. We know that this is 3 divided by x plus 1. And as if you divide that, 3, so we can put 1, I believe. So that will be x plus 1 all over minus, okay, the usual division. So that will be negative x plus 2. So technically then, 3 over x plus 1 is just equal to the quotient 1 plus the denominator negative x plus 2 over x plus 1. If you can remember it way back grade 10, right? The quotient plus the remainder over the divisor. So quotient plus the remainder over the divisor. So instead of writing that, we can write it this way. 1 plus negative x plus 2 over x plus 1 as x approaches positive infinity. So we can distribute. So this will be limit of 1 as x approaches positive infinity plus limit of negative x plus 2 over x plus 1 as x approaches positive infinity. So I believe you know that the answer for this is 1. And what we will be doing here is the degree for both is 1, right? So x to the power of 1. We can just simplify them. So that will be x times negative 1 plus 2 over x times 1 plus 1 over x. Okay, so we simplify that. So it's 1 plus, we cancel x. So what's left is limit of negative 1 plus 2 over x over 1 plus 1 over x as x approaches to positive infinity. So if we solve this one, this will be equal to 1 plus, you solve limit of negative 1 is negative 1 plus limit of 2 over x is 0 over limit of 1 is 1 plus limit of 1 over x is 0. So if you solve 1 plus negative 1, so the answer here is equal to 0. There are actually shortcuts for this, but this is the longer way. This is the actual and the correct procedure if ever we'll be solving for this function. But if you were able to find a shortcut, that's very good. There is a shortcut way. I'll sometime I'll be able to teach you how to do that. All right, so let's proceed to the last example, which is this. So if earlier, when the degrees for the numerator and denominator are not equal, and earlier, if you notice, the denominator has the greater degree compared to the numerator, this time, still having no equal degrees, but the denominator has a lesser degree compared to the numerator. So what we will be doing here, everyone, is we focus on the degree of our denominator. All right, so if this is the case wherein the degree of the numerator is greater than the degree of the denominator, let's focus on the degree of the degree of our denominator. So what we'll be doing is we use the degree of the denominator, and that is to the power of 3. So we apply the pulling out thing wherein we pull out t to the power of 3. So it's t to the power of 3 times. So pull out t, or it's t plus 11 over t cubed. Then what happened here is just t cubed, right? Because it's t cubed. So there is no need for us to pull it out. We cancel. So what's left is limit of t plus 11 over t cubed as t approaches negative infinity. So if you wish to distribute it, so it will be like that, plus limit of 11 over t cubed as t approaches negative infinity. And if you simplify this, let's simplify this one first. This is equal to 0. Now, this is just equal to, on the first concept on polynomials, right? This is equal to negative infinity. So negative infinity plus 0 is equal to negative infinity. So that is our answer if ever you will be solving this one. All right, so basically that's it. And thank you for viewing, and you have a great day.